To access this nugget, you will need to already understand that magnets produce magnetic fields around them, and that we represent these magnetic fields with field lines. You should recall that field lines have a direction, and that magnetic field lines are drawn pointing away from north poles and towards south poles. You should also know that field lines combine when they're travelling in the same direction, for example between a north and a south magnetic pole, and that they will avoid one another when they're pointing in opposite directions, for example between two north poles. This is an electron. You should be familiar with electrons already. You'll know they've got a charge of -1, and that their mass is so small that we treat it as approximately 0, or we say that that's negligible. What you might not already know about the electron is that when it moves, it will create tiny circular magnetic field lines around the path in which it travels. If enough electrons travel in the same direction, for example, when an electric current travels through a wire, then these field lines combine to make a stronger magnetic field. You might have already noticed that the direction of the field lines around the wire are circling in the opposite direction to the direction of the field lines around the electron. Pause the video and consider why that might be. The reason is that we use conventional current, and conventional current actually represents the opposite direction to the flow of the electrons. If that surprises you, consider exploring the topic of electric and conventional current. A useful way to remember the direction of the magnetic field lines around a wire is to use the right-hand grip rule. If you were to grip the wire using your right hand so that your thumb runs in the direction of the current, your fingers will be curling around the wire in the direction of the magnetic field lines. Pause this video and attempt to visualize this yourself. Sometimes we want to look for the circular field lines head-on. To achieve this, we would need to look down the actual wire itself, and that can make it difficult to identify whether or not the current is flowing towards us or away from us. To help with this, we use a cross to represent a wire which is travelling away from us, and we use a dot to represent a wire in which the current is flowing towards us. A useful way to visualise this is to imagine that the wire is an arrow, travelling in the direction of the current. If the current is moving away from us, then we would see the tail feathers of the arrow, and so we would draw a cross to represent those tail feathers. If the current was moving towards us, we would see the point of that arrow, so we draw a dot to represent that point. Now imagine that the wire is running through the field lines that run between a north and a south pole of a magnet. Where would the circular field lines around the wire combine with the field lines between the north and the south pole? And where would they move away from each other? You can pause the video to try to make a decision. We see that the field lines combine where they're travelling in the same direction. This will be at the top or the bottom of the wire depending on the direction of the current and the orientation of the north and the south pole of the magnets. Pause the video here and use the right-hand grip rule to make sure that you really understand what this diagram is showing. Because there is a stronger field above the wire and a weaker field below the wire, then the wire will experience a downwards force, moving it away from the stronger field. If you understand the contour lines on maps, then you can imagine this as the movement from a high gradient to a low gradient. A simple method for determining in which direction the wire will experience a force is to use Fleming's left-hand rule. By putting your hand in the position shown, your thumb will point in the direction of the force if your first finger points in the direction of the magnetic field lines and your second finger points in the direction of the current. Pause the video and see if you can use the left-hand rule to predict whether or not the wire in the diagram will experience a force moving toward you or away from you. If you predicted that the wire will experience a force away from you, congratulations, you can use Fleming's left-hand rule already. If you predicted that the wire would move toward you, spend a little time to try to understand how you might be using the method incorrectly. Now that we understand what causes the wire to experience a force, we can understand what variables might impact the size of that force. So pause the video here and try to identify 3 variables that might increase or decrease the force felt by the wire. Because the force is produced by the interaction of magnetic fields, one thing that we can change is the magnetic field strength between the north and the south pole. We call the measurement of this field strength the magnetic flux density, which is given the symbol B and it's measured in the units Tesla. Since the second magnetic field is being created by the movement of electrons, we can also increase the force felt by the wire by increasing the number of electrons that are travelling through the field. There are two ways we can do this. First, we can increase the current moving through that wire. Secondly, we can increase the actual length of the wire, which is within the magnetic field. We can express this relationship using the equation force equals magnetic field strength times current times the length of wire. From this equation, it's easy to see that if any of the three variables increases, then this will in turn increase the force experienced by the wire. Fortunately, because the symbols we use for magnetic field strength, current and length are what they are, we can represent this using the simple equation F equals Bill. No, not you, Bill. If we run a current through a loop of wire, one side of the wire will experience a force in the opposite direction to the other side of the loop. This is because the current on one side of the loop will be travelling in the opposite direction to the current on the other side of the loop. You might want to pause the video here and use Fleming's left-hand rule to check that you agree with the direction of those force arrows on either side of the loop. Now, let's see what happens when we allow this loop of wire to move. We see that it rotates until the wire that experiences an upward force is towards the top, and that the wire that experiences a downward force is towards the bottom. To achieve a full rotation, we need to find a way to make it so that the wire on the left-hand side is always being pushed upward, and that the wire on the right-hand side is always being pushed downward. A very clever solution to this problem is called a split ring commutator. Split ring commutators are metal loops that allow the loop of wire to turn independently of the circuit connected to it. Importantly, every 180 degrees they also change the direction of the current flowing through the loop. They do this using two metal brushes that connect the external circuit to the loop whilst allowing the loop to rotate freely. When the ring is turned 90 degrees, the brushes pass over the split in the ring and are now connected to the opposite sides of the loop. This ensures that the current is always flowing through the loop in the same direction. In this example, that's clockwise. In turn, this ensures that each side of the loop is always experiencing a force in the same direction, allowing a 360-degree rotation to occur. Combining everything we've learned in this video, we're now in a position to fully explain how an electric motor works, and how it's able to turn electrical energy into useful rotational kinetic energy. You might want to identify some of the electric motors in your home, neighbourhood or school. Spend a little time to appreciate the complex but beautiful physics that is occurring to make each rotation possible.